So I'm just going to do a quick sort of overview of what we sort of discussed yesterday and what we're going to discuss today. So yesterday we started with an introduction to C++. Morris talked through a number of language features and some of the background to the language itself, a little bit of history and a little bit of basic syntax. And then went on later part of yesterday morning after coffee to talk about classes, and some different structs and types and things you can do with them. Yesterday afternoon, I then kicked off after lunch talking about loops, containers, and iterators. And we discussed then some resource management at the end of yesterday. That covered a number of things around pointers, allocators, destructors, and constructors, and some assignment and some idioms. The main thing we got to at the end was an exercise on Morton ordering, which looks something like, if I can find where I've just put it, this. And what we were looking to do was implement a matrix class which organized the data that it stored under Morton ordering. Okay, and there was 2 steps to this exercise. But importantly, the sort of ordering logic had been provided for you in a bits.hpp file, so you didn't have to worry about setting up the organization. What you had to concentrate on was step 1, the construction of classes, and step 2 in the how you develop, how you build an iterator to move between the elements of the matrix in this order. Okay. Before I jump into that, actually, I didn't say what we're going to cover today. So today we're going to go through the Morton ordering example that we will talk through now, and I'll go through the solution to that. We are then going to have a session on templates for generic programming. Have a brief coffee break. There's no example with that one, so we'll just have a short break, and then we'll move on to algorithms, lambdas, and traits, which talks about some of the built-in algorithms, how you can use lambda functions to your advantage, and they nicely work together, and some of the type tracing operations that are available to you in the standard library. We'll then take lunch at the same time as yesterday, around 12:30, and then we will discuss linear algebra with eigen. The simplest thing to describe eigen as is, and it's not a very fair comparison, is that it's the numpy. Kind of can be thought of as an equivalent to numpy. It is not the only game in town in that regard, but if you're looking for a linear algebra package in C++, eigen's a very good starting point. And then finally, after coffee this afternoon, we'll talk about threads in C++. The example with linear algebra for eigen just before that is a little bit more involved, but it does actually produce a nice animation just on a diffusion equation. So in terms of getting used to solvers and things like that and how they might be organized in eigen, that's quite involved. Whereas the threaded example is a little bit lighter weight. So we can probably discuss that together before the end of the session today. Right, that's the plan of attack. First of all, Morton ordering. So this is not the simplest of examples if you're a bit newer to C++. So if you found this a little bit tricky, then don't worry about that. It's meant to kind of give you something to think about and challenge you a little bit. And there's kind of 2 phases. So you've got this step 1, which is the partial implementation of the matrix HPP, and you need to think about how you're going to store data and construct and destruct the matrix. And there's sections in the file marked with to-dos in order to know where you need to make a decision or think about what you've implemented. The second step is you're going to complete the matrix iterator class that's been started. Most of the code's been given, and there's some information about bidirectional iterators you can look up. on CPP Ref. Again, this website is pretty valuable to you just to do any piece of work or look at anything. So really keep this in your back pocket if you've got questions or things you need to understand about C++. And again, things are marked with to-dos for the bits you need to edit. So I should have up, he says, moving things around that aren't what they're meant to be. This is what I wanted. Okay. So step 1 in matrix example, in the model ordering example, we have. So let's go out of here. So I'm just in step 1 files, and I'm just looking at matrix.hpp. So I'm using the same compiler as I was yesterday. I'm module loading GCT/11.2 for those of you running on ARCHER2. Okay, so this is a 2D square matrix that stores data in the Morton order. So this is the Z patterning I've showed a couple of times. There's a simple implementation that requires the size to be a power of 2 or 0, indicating an empty matrix. So we have some requirement on the size. I'm just going to increase this a little bit because it's not the clearest for you on the screen. I know the blue doesn't really help, but I don't want to fiddle around with that right now. The matrix does not need to be resizable, so there's no requirement to do that. And the matrix must not be implicitly copyable, but must use explicit duplicate member function calls. Okay, so this is starting to tell you information about the requirements for the function and what it can and can't do. So we just need to go through our to-do list and tick things off to make sure we're happy with each of the implementations. So we're going to use so let's also look at the tests for this before we do anything else as well. Don't make assumptions otherwise. Okay, so we have Morton matrix, which is some small n. We have a bunch of assertions, and we need it to do a number of things. Basically, we're testing various properties of this matrix, and we're looking to assert that it's valid. Okay, there's nothing particularly unexpected here about the types of tests you'd expect for the different matrices. Okay, can I test it's free? Can I test I can move it? Can I test the large version? Can I test a small version? Okay. Move it, things like that. Okay, so for this, we're going to think about this as a variable. So first thing we have to look at is where our data storage is, right? So we've got some rank, which gives us the dimensionality, the size of the matrix. And then we need to think about the data storage. So before we start implementing other operations, what are we going to do here? Now, the best option here is to think about using a unique pointer. Okay, now we're going to come on to template types later, but I'm going to implement it here for now. This just means that I can take any particular type. Okay. So what I'm doing is I'm saying I'm taking a unique pointer to an array of type T, and that's the data member. It's going to store the matrix, the Morton ordered matrix. So importantly here, this isn't some two-dimensional shape or object that we're storing. We're storing a flat array. And then we have access on that flat array in order to give us the access pattern we desire. Okay. So now we define this, we can think about how we're going to use it. So do we need anything else from the default constructor? No, default initialization is fine, so we don't need to add anything else. So just if nothing gets passed to the constructor of matrix, it just takes a rank of 0. That's fine. It's just an array of size 0, and the rank. There's no data added to the data member, and the rank is set to 0. That's fine. Okay. We need to. However, we do need to allocate memory here to data based on the rank here. Sorry, wrong function. This one here does our test, takes a rank here, but we do need to add to the initializer list now that our member's rank is set to R, and that our data is going to take a new pointer so that an array of type T. You just think of this as int or double for now. It doesn't matter. We'll explain this in the next lecture, but it's important just to go through this example first. And we initialize the data to the new pointer with this size. So now you've got an empty array of the correct size if we get given a input rank to when our matrix is constructed. We then also check that our assumption that it is a matrix to the size power of 2 by doing this assert. Okay. So we then move on to things like the copy constructor. We've explicitly said that they must not be implicitly copyable. So the copy constructor and the copy assignment have been deleted here in these two lines. Okay. Okay, and then we need to think about whether we can have move. So we said we can have move, but what will the default implementation be okay? Unique pointers allow us to move in a sensible way. So I reassign the resources as we discussed yesterday. So yeah, the defaults will be fine here also. Okay, and then the destructor. Will the default destructor be okay? Yes, this will also be okay because it knows how to deal with, the compiler will know how to deal with a unique pointer of an array and the data member. So we don't need to do anything here either. Okay. We do need, however, to provide our duplicate functionality because we said we want to have some way of explicitly providing the ability to copy, but we don't want it to happen implicitly itself. So we can have a new matrix, which is going to take rank, this member as an argument, and that's going to be our output. So this is going to return a matrix when we duplicate it. And we're going to then use the standard copy functionality to put my copy. So we have members data, data to a location data plus size, and then we're going to put this into hands.data get. Okay, and then we're going to turn. Okay, and then we just check through everything else. So we've got something that returns its rank, something that returns the size. Now we've got some operators here that we also need to implement. So this is where we want to manage things like element access. And we need to look at the bit.hpp file that's in the directory above. Okay, and there's a bunch of functions in here that allow us, that are all looking really relatively complicated, but we've got things like compute the two indices from a Morton index. So if I've got an array that says that's the index of the Morton order, then I can go backwards and pick out where the 2 points in the matrix should be. Similarly, there is the equivalent in code somewhere. That's decode, and above it is encode. So from compute the 2D Morton order from a pair of indices in the matrix. So these are the two key functions here: is the decode and encode. Again, the rest are helpers. So if I want to access, so I've got constant element access, and I've got mutable element access, and I'm implementing both. So if I'm going to mess this all up because I'm not here for that. So also, so I can have Z result of encode. So if I've got two indices for the matrix, I can encode them to get the equivalent Morton ordering index, and then I can return the element from my data member data based on this new index that we're calculating. Okay. And there is no difference for the difference here for the mutable access. It ends up being the same. Okay, and then we just okay. Then we have raw data access. Okay, so we needed this for above where we had used to copy. So we're saying a copy from what gets returned from data, and then up to data plus its size, because data is returning data member data, which is a array that's going to be contiguous in memory. So as long as I know that I'm going to return from data plus data as a size, then I'm going to return the entire region of data. So to implement these again, we have a constant and mutable version of both of these, and we can do this quite simply. If I can actually get my tabbing right, with just turn data.get. Okay, and the same for this. Okay, I think that is everything we needed to update for this. Now, of course, when we file anything, it's all going to go wrong. Let's see if it does. Of course it does. So why is this gone wrong? That is a error in error unique pointer is namespace standard does not return template type. Interesting. No memory there. If you spot it, shout out. I have a unique pointer which is data. That is complaining at me. Yeah, I think it's from the. Oh yeah, because I'm being an idiot. Good spot. Okay, and then we just got an issue with this unstated. Did I forget the braces? Yeah, in my example, I've got the memory included. So I didn't think I needed to add that. So this is going to be, I won't be able to access the program function, so I will need to go to this. Okay, so pass all the tests. Okay, that's example 1. Okay, so example 2 involved, and in this case, we've got a iterator to implement. So, fine, this example. So let's check that I've actually got memory here this time. CSR memory history. Yeah, right. So again, we're implementing a 2-dimensional square matrix that stores data in more order. Same requirements, same matrix class. So you can cheat in this example a little bit because you can go look at this because it's fully implemented here. Okay, there's a slight difference though. The copy is looking at the iterator instead of looking at some data or point in array. So there's a slight change in the way this is set up, but otherwise, matrix is implemented in a very similar way as before. So to do implement functions to get the iterator to first and just pass the last elements in the matrix. Okay. So what you need to be thinking about here is to do. I need to this way to begin. So we need to return iterator, which has been defined. So we're using here. We'll come on to this in this templates lecture in a moment, but basically allows you to redefine the type. So matrix iterator of some type T. And this, like I said, this T is a wildcard. It can be double, it can be in, you can choose. But you can, instead of writing out a long matrix iterator of T every single time, you can redo a definition using the using command word, and then iterator is the type matrix underscore iterator of T. Saying we have a const iterator. Okay. So that's quite a nice shorthand. So that's why if this looks confusing, you can't look it up. It's because that's what's being used here. So we're returning an iterator of that type. And to begin with the mutable ones, we're returning an iterator data in that position. So that is at the beginning of our, and then the end, it's got to by returning an iterator data plus size. Am I misspelling everything again? Iterator. Oh, yes. Thank you. Because you know you love me watching me deal with compiler bugs. Compiler errors even. Right, and then similarly for the const version, we have these. Okay, and I've got some data storage, which we had before. Again, I've got my rank as an unsigned 32-bit int, and I've got a unique pointer of some array of types T. Okay, right, and now I've got the implementation of the matrix iterator itself to deal with. So we've got some default constructor that, and we've got some operators to deal with and some private members to deal with. So let's start with the private members, because that's going to help inform what we're doing with the rest. So we're going to need 2 members here. So we're going to need a pointer of this type, which is the start of our iterator. So this is the pointing to the beginning, and we want a pointer to the current location. Okay. And that's going to help us define where we are as we move through this iterator. We then need to do the default constructor. So this can just be like Peter. Can just be, at least that's a sensible default constructor. We must define copy constructor and copy assignment. Decide if the copy, move, and destruct behavior is going to be okay. So the defaults are fine in this example. So we're going to do sensible things, just dealing with them, just and they know what to do with those, so we can leave that. The X and Y coordinate of the current element. So we can calculate this. So on auto Z, we can calculate this with then taking the difference of where we are currently in the array and where the start is, like this is our current location. And then we can use the pack function, which I believe is defined in bits. Yeah. So we've got some way to pack in the pattern. So if we've got so we've got reverse, we've got pack and split. So based on our position in an array, we can work out what our Morton ordering should be. So once we work out our position, we can pack that. And then for Y, we can do the same sort of thing, but we can shift it by 1. But that's just working about our locations in our current element. So that, while how pack works may need you just to sit there and take a minute to think about it, in terms of what we're trying to implement for the iterator class, this makes some sense. We're trying to get these locations out based on where we are in our array based on the iterator. So we now need some comparison operations because, as we discussed yesterday, when we define an iterator, we need to be able to compare iterators. And this is relatively simple in this case because for we're just going to return a dot pointer is equal to e dot pointer dot comparison, sorry, equivalence, and then we can use just a so we can then look at not equals in by just comparing the pointers directly. So that covers off comparison operations. We need a dereferencing operator. So in this case, this is just going to dereference the current pointer. So we just need to return the reference of the pointer we're at. We need pre-increment and pre-decrement or decrement. So in that case, we just pre-increment pointer we're at, and we just return this, the dereference version of this, which is this current object. And then we, for the decrement, do something similar. So we're going to, what this is saying is we're going to make a change to pointer, and then we're going to return this object back. Okay, that is most things. What's something else? We'll need one other constructor that is private, just so that we can so it works. This is created through pointing at things. So this is to be used by other objects. Okay. It was a bit long-winded and took a little bit of time, but that should be everything. I'm sure I'm going to make a mistake. Somewhere. Of course I have. Yeah, I've missed a underscore somewhere. Okay. And also now missed something else. That was, is that my initial constructor? Default constructor. Yeah. Okay, let's build everything and we can test it. Base, we can test the iterator. For the equals operator, are pointer for A and B not private, or can you access if you are past their address? So here, I guess. These are inline non-member friend functions. I think it's the friend that's getting you out of that. so that you can still gain access to private members. But you're right. Normally, you would not be able to access because they are pro members. So yeah. Right. I've rambled on about this example for long enough. Now, this is not the simplest example, but it's a quite nice way to get you to do something and create your own iterator through something that's non-linear. And if it's something you found a bit tricky, to go back over and just look at the example. The solutions will be posted at the end of the course if you've not already found them. So do have a think again. And it took me a couple of just go throughs just to get the sense of that. So we're now at sort of 10 past 10. My plan was to have a coffee break at about 10:45. So I'm now just going to go through templates and kind of explain where some of where this magic sort of T came in to the discussion, and why that's actually a really smart thing, and why we care about using that. So there's only 14 slides, and then we'll have a coffee break. So templates. That's what this little T means. And what's the motivation for templates? Templates are a method for doing meta-programming, a program that writes a program. Okay, so an easy example for this is if you have to implement sum for every single type, you can see that this is going to get very laborious and people are going to make mistakes very quickly. Even with just a couple of these, it's already looking like unnecessary duplication. So I could also need to have a float. I need an unsigned. What about the complex class we discussed earlier? It's going to be boring and hard to maintain. What would be better is if I had something like a template function. So now, instead of writing out a copy of this for every single case, we can instantiate this template for a particular type by just passing in the angle brackets and the type that we want this to be used for. And in this case, this then means I have something that I don't need to maintain every possible type for this, and I can just write one copy. And all that's happening, and we've kind of already been using this when we were using some of the standard template library in standard vector or array, for example. And we passed in int or double or whatever else. And the point is the vector was making underneath it was making a C-type array with of particular type, like we just showed with a unique pointer, and that T in square brackets in the more ordering example. And you can see this can be very useful because now I've just reduced all the different variations of code that I need. In on-compile time, my compiler will come along and apply this for us. It can do some compiler deduction. However, I'm personally not the greatest. What this does is it hampers readability about where your function is, because people may make an assumption that if there's a sum without the angle brackets and the type, that it is not a templated function that's being called, and it could generate confusion. So I think I personally prefer being explicit here, but it can do compiler time deduction of the types if it's relatively easy. It's not going to do this for overly complicated things, but it can make a good go. So in addition to templated functions, we can also have templated classes. The point of a sort of templated class here is in the same way, but now we have some class T that we can take the template, and now that's available for the whole class. So in the array example we gave before, I think we had an int. What was it under? It was under. Anyway, doesn't matter. I'm going to read also. Compare this to the myArray example we had yesterday, see there's no, you can see the difference where we had to add a new template class T on the top. You'd have a particular array, and this would be default to double. So now you can see that instead the data pointer to the data, the pointer data is a double pointer hard-coded in our implementation from yesterday, but with the template case, we can have any type here instead. Okay. And this means it's very flexible, right? So you can now have one container implementation that's maintainable that can be applied for lots of different types. You don't have to duplicate code, and it cuts down on the possibility of errors, especially when you're writing complex classes. You don't particularly want to have to re-implement the thing for every single type possible. And as we were just using in the modern ordering example, you can redefine the names of particular types with the using command, so that, and the main use for this is to reduce very long, complicated type names to something that's more readable. The only thing here is to be careful of is not moving this definition far away from the code that uses it, else it leads to confusion about what type is actually being used. What's often worse is if you define these and then you also have odd names for your template arguments. So there's nothing here that says that this template class T has to be T. This could be template class, as long as it's not one of the protected types, it can be pretty much anything you want. You can also have multiple of them, but if it's not something kind of clear and obvious to the reader, like T or some other single character that you're expecting to be replaced by some amount of compile time, and you give it a name, it can confuse people to thinking that this is actually a defined type when they read through the body of the code. So just be, and if you then confuse it with your own named types using, it can generate confusion for other people. So just be careful about the freedom this gives you. Is great because it makes your code more readable, but only if it's clear. So try to pick a convention about what you are using for types in this case, and that way it's much easier for other people to understand what you intend by this. So for example, I don't like this having iter. I'd want iter_t or something that means that it's clear to the to other people that this is a type. You can have using declarations inside classes, and this is very nice for exactly as we just showed in the modern ordering example. We can have we can name different types for the template so that it has meaning associated with the different types. So instead of just having to remember that this is a reference, we can just call it reference. Or having a const reference, we just call it const reference. And therefore, semantically, you might have to do a bit more typing, but if that makes it more understandable about what your intent is, then that's a good option for you. Just pick a convention with this and stick to it. But this is again good because you've got this use of using close to the code that's using it, and therefore it means that you're, as you're developing or working with people, they'll be able to understand what your intent is. This is important, this bit. So where do you put your implementation? So templates are not executable code. They tell the compiler how to create executable code. So the definition must be available in the translation unit of the user of your template. So typically in a header file. So what that's really saying is that if I use a template class or template function somewhere, I must make sure that where it's used has the definition available to it, so the compiler can find it. You can do the definition of the functions in place, or the end of the header or equivalent, another file that you include in your header file so that the definitions are available at compile time. So the other issue here is the one definition rule. So I don't think I said this yesterday, but I probably should have done, is that everything used has to be defined exactly once. There is 2 exceptions: templates and functions marked inline. These can have many. Again, these can be repeated in many translation units, i.e. separate invocations of the compiler. At link time, so once you've compiled the code and then it's linked, the linker will arbitrarily pick one definition of these templates or inline functions to use. So you need to make sure that the implementations you provide are all identical, as you're leaving it up to the linker to make a decision about what your code does. And all this practically means is that you need to have one definition of these things and keep all of them sensibly. Do not duplicate them in your code, as it can have difficult consequences that you may not notice and may not flag as wrong from the compiler side or the linker. Okay, so templates and type deduction. So again, if we go back to our little sum example, I can have a template class T that returns type T and is a sum of a type TA and type TB. When used without specific or explicit T, we can get, it can interpret what the types are needed from the inputs. So here it knows that the type being passed to type T being passed to sum is an int because X and Y are ints. So this is the compiler doing template argument deduction at compile time. This means it examines the types of the expressions as given as arguments to the function, then tries to choose T such that the type of the argument and the expected type match. Okay. Again, you're leaving this up to the compiler. Compilers are great, they do a lot of very good things, but they are not magic. They are other pieces of code written by humans. So be slightly wary if you want explicit behavior. Obviously, obvious things like this should be fine, but if you're trying to do more complicated things, it may be better to explicitly define this. Okay. So it's important to note the template parameters T and the type function arguments might be different, but related. So for example, here's a number of void functions that return voids, but the template class passed as T, but actually the function arguments taken are of different types. So at the top, we just take by value in the function f. In the second row, we are able to say we're taking a reference of x into this function, and that's just t ampersand. We can have a constant reference of this with t const ampersand, but you see you're applying an effect onto the type. This is something you can do if you just put int there and it makes sense. We have then our forwarding reference, but you can also do more complicated things like pass t to standard vector. Standard vector knows how to deal with a type passed to it, that's because standard vector is a template, is templated. So this can kind of grow and you can build up various type structures like this. But again, they're all related to T, so they're perfectly valid. And which you pass in will affect the deduction of the argument type. You can also parameterize templates with non-types, if that makes sense. So you can pass certain values into it. These are all the examples given here are in integers. It's probably the most useful one, and we'll come on to that in the eigen example. We sort of saw this with the array example yesterday. An example of it, at least. Let's find that. So here we have a main function which is just, again, it's using the using to redefine our standard array to grid point, but that's not what we're interested in here. Standard array is taking an integer as its type, but also 3 as its size, but it's being passed into the template as a template parameter. So that's an example of this being used in the standard library. Where when we come to discuss eigen, we will use this quite a lot, and the examples given below will kind of follow later on. Is that you're going to pass some integer n in to define some size, or into a matrix to find the number of rows and columns in the matrix. We can also do this with operator and things like this. So there's, again, you can layer this, is what I'm trying to say. So you can then pass these in, as we've just seen with vector above. Vector took a template T. This has to be an actual type. That's what vector's expecting, but the matrix might take the sizes in. Okay, and then C++20 floating point types and little types can be taken as well. So I'll put on that bit. The full rules are quite complex for type deduction, and you can find them up on this link. But usually you can ignore these and just think about whether you want to copy an argument or not. If you don't want to copy out a reference, whether you can handle the const argument, if so, add the const qualifier. If you want exactly the type of the expression, if so, double ampersand, and there's a folding reference. But you apply this to type the template types as well. And then finally, the auto keyword follows the same rules as template argument deduction. So you can use auto with your templated classes and functions as well. Right. That is where I wanted to get up to before coffee. We're running about 15 minutes early, but that's okay. When we come back, what we'll do is we will stop now. There's not an example with the templating types because it kind of follows from the Morton ordering bit. We'll take 15 minutes now. We'll come back at, actually, let's have 20 minutes now. Let's come back at 10 to 11. And then we're going to start looking at algorithms, lambdas, and traits. And there's an larger example at the end of this, which will take us up till lunch. But we can give everyone some time to go through. Before we do, are there any questions? Okay, as there's nothing jumping out to people. The important thing here is with these template examples is to just play around with little example pieces of code like this to understand it. So what I'll do is I'll leave this up. If people want to just run a small implementation of that in the 10-15 minutes you've got now till 10 to 20 minutes, do and see how that works and try it with different types out, and that could be the short example for this section. Okay, back at 10 to 11. Okay, just before we go on to our next lecture, I just want to discuss that sort of mini exercise that I just suggested people look at there. So here's kind of my little example of the use of this template function sum, just to kind of illustrate this a little bit better. So yeah, we have a template class or type name is used interchangeably here for T. We're returning the same type of the sum of these two types. It doesn't have to be true. You can return a different type. You can return void. But if you're returning the sum of something, they both have to be the same, and the return type has to be the same. I then just have a simple example where I'm going to have two ints and sum them using sum int, and I'm going to have two doubles and sum them and return that double. You can do much more complicated things as we discussed with various other types, but one thing I didn't mention that I felt like I should have done is that if I were to make this type vector of int or vector of double, vector doesn't have an overload for the addition operator by default. I don't think, but say it doesn't. It will fail. It won't know how to do the operation to add two members of vector type. So one thing you have to be very careful of when you're starting to do this is that when you're using templates, you may be able to pass them in thinking it's going to be okay, but they need to be able to, those types need to be able to perform the operations required of them when they're used. So this can mean that overloading operators for a given type that you create may be necessary before certain functionality will be available to you. So if you want to make your own custom array class type that we discussed yesterday, the myArray, we could do that, and then because we know there's going to be fixed size, we could implement an overload for addition in order to enable this sort of usage. But it's just another something you have to think about when you're starting to define your own versions of these objects. Although you wouldn't do that. What you'd probably do instead is look at a package like Eigen, which has done some of this for you. Okay, that was a brief aside. I just wanted to give you guys an opportunity to try and have a go at that as just an illustration. And show you. Oh, I should actually prove that this code works. Compile and run this. Yeah, so I'm adding 1 and 2 together, and I think 1.5 and 2.7 together, and that gives you the right answer. So that does compile and run. Okay. So now what we're going to focus on up until lunch, and I think what we may be running a little bit faster ahead of time, so we may take an early lunch and let you guys have some time to think about this example. Yes?
Oh, sorry. Yeah, we have a question in the chat. This one.
To put the overloader plus for vectors within the template. Then I'd have to carry around with where I'm using the particular type or the functionality of the type if I did that. So you want to keep the overloads. I think you have to also keep the overloads within the vector class, for example. So you're right. You're thinking about, well, maybe instead I should just write a function which does addition that for every case. But I don't know all the cases. The point of this is I don't know all the cases in which some is going to be used, and I'm not restricting that, and that's by design. So actually, I should provide the. I should keep the way to manipulate my types with the type itself. Is the logic there? You're right. It does limit you because you could end up in situations where you're expecting certain functionality to work and it doesn't. But at least then it should give you a sensible compile time error. Yeah, it being these template functions or classes give you this sort of a level of being generic, but it does mean that it's not kind of defined what it won't do. But yeah, good question. So, okay, we're now going to talk about 3 things. Algorithms and lambdas are going to be the main focus, and then we have a little bit on traits at the end. At the end of this, we're going to have a longer example, well, about the same size as the Morton ordering example, but I think a bit easier than Morton ordering on algorithms and how you can use them for a particular example. But I want you guys to have kind of lunch to look at that because it's a little bit, it's worth going through. It has multiple stages that depend on each other, and we'll go through probably afterwards. So I think we will start that before lunch and maybe finish it afterwards. Right, let's recap. So we've discussed a few times about how to iterate in these lectures. We have sort of old C-style iterations. Old's not fair, so that's it's C-style iterations where you have some value defined and some end condition and an increment. Okay, and you iterate through by specifying a location in the data. You have older C++ style uses of iterators, which hides some of the details and uses an iterator that's defined in your data type. So as we just saw with the Morton ordering example we just discussed, as the example from yesterday and we went through this morning, we defined begin and we defined end, and we have an iterator which is some pointer at a location which knows how to move forward and back. And we can dereference this, and then we can do updates to it, and that then persists because we've done the dereferencing with a little star on the pointer on the left-hand side, that central block. And then we have newer range-based for loops, which basically says, well, I know if I've got data and it's got some range, and if it's got the correct functionality, I can just iterate through this and take individual items. In this particular example, I'm taking a reference of the items within data so that when I edit them, they are updated. Okay, and those are all fine. But what we also have is the standard algorithms library. Quick question on the different fors. Do they perform identically? Is the range-based for just hiding the fact that the item data sort of thing? It's more, I think it'll be up to compiler implementation. My expectation is going to be act like it's hiding. It's more that it's going to hide sort of the middle one with the iterators. But you don't need to explicitly access it. And the difference between the C style and C++ style is you're using information about the construct of an iterator that knows how to move between elements in a container, but C doesn't have the concept of a container at all. So while it looks like you're doing the same thing, there's actually different concepts happening here. And the key difference between C and C++ is the containerization. The compiler may turn this into very similar things, and we may well look at that momentarily. Okay. Standard algorithms. So we have something that's on. We have another way to do this, because as Morris was discussing yesterday, if C++ knows how to do one thing, it's to add multiple ways to do the same thing. So the standard algorithms library includes many, about 100, probably more than when these slides were written, function templates that implement algorithms like count the elements that match a criteria, or divide the elements based on a condition, type logical statements, okay? These all use iterators to specify the data they will work on. E.g. count might use a vector's begin and end iterators to know how to do the counting. So we have a little example here. So we include the algorithms library, and we have some vector of data, and we read some values into data. It's just a vector of ints, nothing we haven't seen before, but it's not specifying what the values are. What we're doing is we're saying, I want to count the number of zeros inside the vector that is called data. So I'm going to call the standard algorithm count, and then I'm going to pass the beginning and the end pointers to count. Sorry, the iterators for the beginning and end of count. And count is going to take a value that it's expecting to match in order to count them. So in this case, it's 0. This allows you to go through and count up the zeros in a single line. So you could imagine this has saved a lot of code there. You would otherwise have a for loop. You'd have to then do a if statement to test if it was 0, and then accumulate that answer based on the if. You could also have things like count the number of primes. If we have our is this a prime function, as we saw in this example yesterday, we can go through the vector data and check, and if it returns true, so is prime function needs to just return true or false, it will count based on if that returns true, and then accumulate n primes and then count the number of primes available in the data. So this is all very useful because this has made our code look very simple. So a possible implementation, this isn't exactly how the standard library does it, but you can kind of view it a bit like this. This is a little bit complicated, but you've got some template class with two arguments. You've got some input iterator and you've got some unary predicate. Okay. Unary meaning one argument and predicate meaning Boolean valued function. So this unary predicate is going to be some function which takes a single argument that returns a Boolean value. So for the if count example, we're going to return some pointer, and we're going to take the input iterator at the start of it and the input iterator at the end, so we know where to begin and where to end, and we're going to take in a unary predicate function which is going to be called p, which is going to return true or false based on its operation. The answer is then set to 0 initially, and we're going to go through from first to last. We haven't looked at the syntax, but you don't need to define the initial value here in the iterator because you know where you're looking at first. So they've omitted this in this sort of old C++ style. And they said as long as first doesn't equal last, increment first. And then we're going to do our test, which says P, our unary predicate, our test is going to return a true or false. It's going to act on the dereferenced value of first. And then it's going to, if it's true, it's going to increment the answer. So it's going to do a count. And then it's going to increment first again, until we've got to the condition that first equals last, and then it's going to return our answer. So this is one way that this countif could be implemented and deferred. But you see, you're hiding a load of a whole for loop and if statement stuff in details that otherwise you would have to explicitly written into a function or your code. Instead, you've got this in the standard library. Okay, so there are a number of key algorithms, and the best place to look this up, as ever, is CPP reference online. But there's lots of things that you can do. So for each, you can apply a function to each element in the range. Count if we've discussed, you can return a number of elements matching the condition. Find if, return the iterator of the first element matching the condition, or the end if no match. So we kind of looked at this yesterday with, I think we had a call to find in one of the examples yesterday, but you didn't know you were using a standard algorithm if just doing a search through a vector. Copy if, so copy input range if the predicate is true to a destination. Okay, this allows you to do the move. Again, we looked at copy earlier today in the modern ordering example. And we had that structure. We had data to return the pointer to data, and then we had data plus size to return the end point, and then we had some output location, which was answer in the modern ordering example. Transform is quite interesting. Apply the function to input elements and store in a destination. Has an overload to work on two inputs at once. Okay, so this could be quite nice if you need to act a function and change and do an operation on a containerized set of values. Swap two values. This is used quite widely. You may wish to provide a way to make your types swappable. So CCP reference. We're not going to go into too much detail on this, I don't think. Sort is another obvious possibility here. Sort elements in ascending order using either the less than or greater than operator, or provide a binary or the binary predicate provided. So you want some way of sorting and determining one to be greater than another. So you can define this sort, or the way you wish sorting to happen, by defining your binary predicate. You don't just need to use their value. So that could be quite useful if you've got some property of a vector of your own type and you need to order them based on some property. You might just have a function that tells you which one's greater than the other. It's built into the function itself, as long as it returns a Boolean at the end. And then lower and upper bound, given a sorted range, do a binary search for the value. Okay. So these are just a set of the possibilities here, and these are quite useful ones to think about for the example later, for the end of this lecture. Okay, so one of the simplest algorithms is the for each. Apply a function to every element in a range. Okay, so why would you bother with this? It clearly states your intent. You cannot get off by one error. So it's clearly states your intent means it's very clear to someone else when they come along and look at your 3-year-old code that you haven't touched in a while and need to edit it, what you actually meant to do. If you have a big for loop here, it's not going to necessarily communicate what you're intending until you've gone through the details of the for loop. If you have just a thing that says for each, you know you're just going to apply whatever this is to each of the elements, and that's going to update them, and you move on. It cannot get off by one error, so you cannot skip elements. That's quite useful. It works well with other range-based algorithms. Concise if your operator is already defined in a function. However, often a range-based for loop may well be better just because it's quite simple for what you're doing. However, something like transform is a very powerful function with 2 variants. One takes a single range and applies a function to each element and stores the result in an output iterator. So here we have some input first and the input last for the first iterator for the input. And then we have an output iterator with our destination and the beginning of it, because the assumption here is that the output must be as large as the input. Okay, so we don't need to also provide a last because we know at least it has to be that size. So we can iterate on the length of input and then output will be okay. And then we have a unary operator, which allows us to do, so a unary operation allows us to do something to that input and place it in the output. This is basically equivalent to the map function from functional programming or map reduce. So in this example, we have a vector of floating point data we've gotten, and we're going to transform it by doing our double in place. That's the standard thing. So we have some function that does double in place. It's going to act on data begin. The nice thing here as well is you can have your input as your output location, and that's okay. So if you don't want to have to allocate some additional storage, you don't need to. But you can see how this is much easier and quicker than some of our other examples that have been used double in place. We just need to define the function somewhere. Okay, so motivations. The implementations have been written and tested by your compiler authors. The libraries may be able to do platform-specific optimizations, and this can be quite important. If you can take advantage of people spending a lot of time optimizing a set of algorithms, that's usually going to get you better performance initially than some optimizations you want to do and that you then have to maintain. Okay, and that while it may be a little bit faster, is it maintainably faster? Is it portable? Or are other people going to do that work for you for their own systems? So vendors will often make performant versions of it for their hardware. You're probably going to struggle to beat them. It's not impossible, but is it worth the time and effort and energy to try it? They form a language to communicate with other programmers what your code is really doing, and this is probably one of the most valuable features. It's around the readability of your code, and it's nice code that you don't have to write. So here's an example of doing the same thing with the for loop explicitly and the condition, and instead versus a copy if you're just using the copy if algorithm. And of course, we're checking whether a set of images contain images of cats. Okay, that's algorithms, but we also need lambda functions, and we'll come back to why they're very useful with algorithms. So your algorithms, they need functions. Very many of the algorithms just discussed need to provide a function-like object as an argument for them to use. So that's that unary predicate that's going to return a Boolean. If you have to declare a new function for a one-off use, In an algorithm call, that's inconvenient and moves the code away from its use site. So we want to keep where the code and where we're using it close together, so it's very easy to understand what's happening in the code. Worse, you would have to create a custom function object class each time. And this is because if you want to capture information, you need the unary predicate to be a callable function, not just as an object you can pass. Okay, and if you have to define this each time, that's not very good. So a verbose example of this, I could have a structure that squares and adds a constant float to a value. Now I have a constructor that takes in the constant float, and I have an operator, the function of operator brackets, that takes in a float x that's to be squared. And I can then call this, so then I have some function that's going to run this, and I have an answer. I resize it to the size of my input vector x, and I'm going to run a transformation operation on this, which says I'm going to begin at x and I'm going to end at x, and I'm going to place my result in answer, and I'm going to apply square and add constant, okay, which has the ability, is callable because it has the operator available to it, and that means is that every element in x is going to go hit this iterator of x, it's going to dereference it, it's going to call this operator defined in this class on the value, and it's going to update and put the answer into the answer vector. But the important thing here is, in order to pass in the constant, you have had to make the whole class, because you need the ability to construct and place C as another argument. Because remember, this is unary predicate, you can only take one value. So if I need to pass other things in, I've got to have all this construction. I have a whole new class for this purpose, which is not ideal. So we can use lambdas to the rescue. So a lambda function is also known as a closure, is a function object that does not have a name like functions you have seen so far. You can define one inside a function body, you can bind them to a variable, call them, pass them to other functions. They can capture local local variables, either by value or by reference. And this is probably one of the most powerful features. They have a unique unknown type. You may have to use auto or pass them straight into a template argument. Can you pass normal functions in C++? Probably by a function pointer. But the issue here is that you need them to be callable, so it can't just be a function, because you'll have had to have called the function to put it here. The point of these lambdas is that you can name them to a variable, and then they can be called later at some time. So a less verbose example would be to have some function that we're going to call, but oh no, sorry, this is the example of the lambda. So here we have to find a lambda called funct. It doesn't have to be called funct, it's just to make it clear that this is going to look like or act like a function. We are using our capture to capture C from the local scope, and this is looking like the constructor we had in the previous example. We then pass in we're then expecting, when we call the funct, to expect an argument which is a double, which is z, and then this is the function body of the lambda, which is just in this case, is just a return statement. Okay. We then can call transform on this, as we did before, and have funct here instead. And then funct, when it's used, will take in elements of the vector x based on the iterator, and that'll pass that into this location. But C has already been captured, and it's being captured by value, so it's going to make a copy of C. That's fine for this because C is very small, it's just a float. It's not going to be a big overhead, but it means we can pass more than the value in. A simpler, less verbose version of this would just be passing the lambda straight in. You don't need to necessarily assign it to a variable. In this case, you're just using it where it lands. You're not going to use it anywhere else, then do this. Okay. Right. So the anatomy of a lambda, we have captures, which are the square brackets. So this is new syntax indicates this is a lambda expression. There are a number of there's lots of funky things you can do with captures. I'm going to focus on 2 today, but again, look at CPURF if you want more information. You have an argument list, which is actually what's going to be called. You don't just have to have one. For use with the algorithms, we have one argument, but you can have many. You can advise what its return type is going to be. So in C++ syntax, to specify the return type of the function, it can be skipped if the return time is void or the function body is only a single return statement, but you can give it this hint. You then have the function body. 0 or more statements is normal. So a 0 or a comma separated list of captures. So this would just be empty brackets for the captures. If you didn't have anything to capture, you can still call it. You can capture value by copy, just by putting the name in the local scope, or by reference by using an ampersand before its name. So ampersand local. So that could be, in our example above, this could have been ampersand C. That would have taken a reference to C into this lambda. Okay. So this creates a function object that's uniquely named, has a unique unnamed type. You must use auto to store it in your local in a local variable, or you can just use it directly in the example shown. You can call it like this, just call function, and then call it with the brackets operator. So note that because it does not have a name, it cannot take part in overload resolution. So it's not going to replace other functions with different argument lists and things like that. Okay, quick, what does this do? Answer in the chat if you think you know what this will do. Clearly, I put you all to sleep. No, no one? Hazarding guesses? Yeah, it does nothing, exactly. So you have you are making a lambda with no captures, with no arguments, with no function body. I can grab it, and then you are calling it instantly. Yeah, it does nothing. Okay. So uses of these, STI algorithm library, as we've been discussing, or similar, pass one of small pieces of code in freely. So here I have a sort, and I've got 2 sets of molecules. Sorry, I have a vector or a container of molecules, and I am going to define a lambda that captures nothing, expects a constant reference to each of these because we're not editing them, we're just comparing, so these can be constant. And then we return a Boolean value based on the comparison between the charges of each of these. Oh yeah, of course we have. Okay, let's just go over that to make sure it's clear for everyone. So a capture in this example here, this is a bit verbose. Let me see if I've got a. No, let's just do it here. So what a capture is saying is that in my current scope, there are values that I can access. And I would like to take either a copy or a reference to them into the body of my lambda, which is in a different scope. So instead of passing in an argument, I'm going to have some some values that I'm going to store as part of the function. It's a bit like in the class example, you could have data members that are initialized on when the constructor is called. In this case, you can store information in a fixed way. Sorry, not necessarily in a fixed way. You can store data or references to data that you want. That's not going to change. So if you call this multiple times, but the set of captures are always staying the same, then your lambda is simpler. Okay. So the point, the example here it's really about it's kind of about locality of the function you're trying to find. So the lambda allows you to do this. If you're calling something small and repeated that you only want to exist for a very short amount of time, in the algorithm example, it means that you're able to do stuff like this, where you can capture certain bits of information, you can allocate it for a particular operation. If you had a large library of functions or lambdas you had to go call out, you're making it harder to understand what's actually happening. And if this is only small, then you don't need to do that. That's kind of the argument. But the key thing here is that it's more, I don't want to say a definitive statement because I'm sure it depends on compiler somehow or some optimization level, whether this is truly inlined at compile time. I imagine it is in some way. It probably means you don't have to move stack frame if I'm thinking about it carefully. But how much that overhead is something you actually care about, I'm not so sure. The point of, sorry, just to finalize, try and cover off this question around captures versus arguments. Yeah, I mean, it's up to you. The example here with standard algorithms, you need something that looks like a standard function, but if you want to pass additional parameters into it, it has to take a single argument. So that's the motivation here. Oh, has this done the usual thing? I mean, so it looks like this one. I remember the last of this course, and I haven't updated the slides clearly. Crossword line. Yes, it should be. There should be an F here. Got connection issues. Apparently, it has returned. Good. Okay, so looking at this example, so if we were going to do this, this is what you're trying to avoid basically, is if in this particular example, when we're using these algorithms, we don't want to have to pass in, write a whole class or struct just to capture C as in the constructor so that it can be used when we square and add a constant. That's a lot of machinery that you're not going to store near this code in a separate library somewhere that you're not going to have access to when you're just reading through it. And it's unnecessary to have all this code here, but instead you can use a lambda to make this much simpler. That's the motivation in this example. And therefore, the capture is acting a bit like the constructor initializer list. And that's why it's different from the argument here, because this argument for the double Z is called every time you call the function, whereas the capture is not. The capture is now just a fixed value or a reference to a value that you're going to use later. Can you template a lambda function? I am unsure, and I will come back to that later. And I will have to look that up because I'm not sure if there's something in the slides about that. there shouldn't be any reason why you can't have an argument with a template. But does the template come through because it's not a traditional function object? I'll have to look it up. Right, I've got slightly sidetracked there. So thank you all for being patient. So we've been through a little quick quiz. Sorry, use. So go back to uses in the standard template library algorithms. So we can do things like generate a comparison or some complex initialization. So this is another use for this, where you want something to be const, but you need to generate the initialization. So this is the bottom. So I want a constant set of randoms. It's auto because it's going to be a lambda generating this. We're saying we're going to capture some size by reference from the local scope, so the local region of code. We're passing no arguments to this. So this is fixed. So we can't change this because once this has been created, you can't change the captures, and we've got no arguments. We know what it's going to return because we're revising it to return a vector type. We have a standard vector of float, which is the answer, and then for every element in the answer of some size, we're going to call a getRandoms function that we have. But once this is completed and returns, so notice that we have the parentheses here, we're calling it instantly. We're not returning a lambda here, we're returning the vector of float, which is the answer result. Now that's been able to generate a set of random numbers that's fixed and that are now constant and that cannot be edited, so that in the rest of the program is not something that can be sort of edited, which is really important when we're dealing with random numbers. So that's another example of a use case for a lambda outside of the algorithms for doing these interesting initialization type pieces. Okay, some rules of thumb. Be careful what you capture, really. If your lambda is used locally, include the including being passed to algorithms. Sorry, capture by reference. This ensures there are no copies. It ensures any changes are made are propagated to the rest of the local scope. If you use the lambda elsewhere, especially if you return it from your current scope to be used in another location, because it's just it's just assigned to a value, so you can return them. You want to capture by value, because if the references to local values become invalid after the end of the current scope. So if you were to return a lambda from a function that had captured by reference, those references would not be usable later on, and the lambda would do something undefined. So the references to another objects may still be valid by the capture, but it's hard to keep track of whether they are. You need to be careful. The other thing is lambdas are meant to be short pieces of code. So unless it's sort of roughly 10 lines, if it gets more than that, then you should really think about moving to a full function or a functor instead. You shouldn't be writing long things in lambdas. It should be short bits of code to help readability. Right. I said yesterday we talked about performance, and someone asked a question about this earlier. So we have many ways to iterate. Which is fastest, which is the thing you will care about, right? You want your algorithm to go quickly. You don't want to spend a long time waiting for your code to complete, and you want to impress people by having really efficient code. We have our 4 now examples, our C-style iteration. We have a old C++ style with an iterator. We have our range-based for loops, and we have an algorithm that for each does a double in place. Okay, and is there any overhead? So we'll quickly compare the implementations to scale. So we're going to run them in loop many times on 1,000 elements of data and see what the results are. And the important thing here is this -00 at the top. Okay, this says we are passing -00 to the compiler. The compiler is not optimizing anything. then C style is actually fastest. Depending on the number of elements, it's consistently faster than everything else. And actually, the iterator style is the next best, probably because it has some optimizations built into for the particular library. You then have, the iterator style is the older C++ style. It doesn't necessarily have any compiler-specific things. The algorithm style is then probably best until you get to very large numbers, and then finally the range-based for loop is actually the slowest in the sort of 1,000 region of elements. But nobody compiles with O0 because you're just going to get poor performance. You're telling the compiler not to do anything. But when you compile with O2, actually everything is much for muchness, and in the larger cases, the C-style for loops are being beaten. And the range-based style, the range for loops that we see in the more modern C++ are slightly slower. So actually, up to a larger number of elements, around 10,000, you may actually see a benefit from an algorithm approach than the others, or as good a performance in the algorithm approach than maybe the range-based style that is the most similar. So just keep this in mind. And again, this is just an example test. This is not the definitive word on performance comparisons of for loops. This is an indication that compiler optimizations are important, and that you're not losing massive amounts of performance by making something more readable to you. But then also do your own comparisons is really critical. Okay. So we've talked about lambdas and algorithms for a bit. A final section before we got to the example today, and I think we will take lunch around 12 to 1 today, just to give us a bit more time in the afternoon, and time for you guys to go away and think about the example at the end of this section, is traits. So C++ generic programming techniques is used, and it's used across the standard out library. It's basically traits of the if then else of types. So it allows you to do type comparison. Provide template class that has type defs and member functions that specify the configurable parts. So your generic algorithms then use this class specialized on a particular type. So it allows you to start specializing depending on the type you get, and ask questions of the type being provided to some template, to some templated function. So it allows you to perform some. So I think we had a question earlier around where should we put certain operators? Should we associate them with the classes that define the types, to define a particular define a particular container like vector, or should we keep them with some templated function which uses them? And the argument there was that we should keep them with the type, and that the templated function that uses them may fall over when we use, even though it can accept them, in theory, it may not be able to use them. But this type of type trading may allow you to restrict what those templated functions can actually use. So it allows you to select behavior. You don't have to change the source of either the algorithm or the working type. You can just do selection based on these type traits. Okay, the several headers contain these. The header type traits is has a lot of information for handling types, e.g. to ask, is this a pointer type? So if you run this on an int, this would give you the value of false. Int is not a pointer type, so it returns you information like that. You also have things like numeric limits of types. So you can pass, the key place you'd use this is if you pass in the template parameter inside a class, you can use it to evaluate things. This is really important on things like numeric limits. The definitions of what double and long mean on different hardware is not set. It's just bounded. So you can start to probe information like that on how the built-in types are actually expected to operate, such as the largest and smallest values, or whether they're integer or floating point types inside your own code. So that's quite valuable to be able to do as well with these type traits. So other traits used everywhere behind the scenes for efficiencies inside the standard library and can be quite useful. So we're going to talk about one real example. We're not going to go do an actual exercise on this, but we're going to just discuss this through. It requires to think about MPI a little bit as the example, but it's not really talking about MPI. So if you've not heard about the message passing interface or the wonderful world of MPI, don't worry, that's not the point of this example. The idea behind MPI is that you can send information between two different processes, potentially on two different nodes. And the key thing here is that to do its sending, MPI has its own set of types. One of them, for example, is MPI float or MPI int. And the key thing here is this is different from the C++ float or int. It's its own distinct type because it needs to carry additional information around what it's sending. And we could have, and in MPI, you have the concept of a communicator. And all a communicator says is, where am I and where am I sending stuff to? And what are all the different, basically, what are all the phone numbers I need to pick up and call to send information to different people or different processes? And it gives each single process its own unique ID, and that's its rank. And by having the rank of another process, you can send information to it. That other process needs to know it's expecting to receive information, but that's how communication operates. So in our little com class, we have a send function, and that means that we can have some the object world, which is holds MPI com world, which is the full set of addresses for the entire community, all the possible ways to communicate. I'm going to send some data, which is just a little bit of a vector, across to another rank. And we'll give it some tag, and tag is just a label, nothing more. Just to make sure you can make all these things unique for debugging and things like that. And then the implementation of this send might have a number of elements. Okay, so we're going to send some constant reference of a data, of an object data. It's going to have some destination, and it's going to have some tag. Underneath, it's going to call the MPI library MPI send. We're going to reinterpret cast. We're going to cast our data to be able to send it. We're going to send the size. And most importantly, we're going to have to specify the MPI data type we're sending. So that's the MPI float or MPI int. But we've not set it here because this is a templated so that we can send it specifically so that it's free to send any set of data. But we need to decide on this data type that MPI is expecting to send. Else there's going to be a mismatch between the two. And it's going to not be able to send our data and probably fail to compile. And then again, we're going to send some destination, we're going to send the tag, and then we're going to send the communicator with a set of addresses it's going to look up for what the destination is. But how do we fill in this right type? For the types in the standard, we could provide a specification for each one. So we would basically lose the ability to template this and remove this class T, and we just provide specific implementations for int, and then we provide MPI int here, and we have to write them out for every single possibility, and this is quite verbose, and that's not very helpful, really. You can do it, but it's going to be long. You're going to have lots of duplicates, and it's going to be a pain to maintain or make edits. You have to edit every single one when you make a change. So basically, you end up, say there's M types and there's N MPI calls, because now that's example we've just given is just for send. There is a whole bunch of other MPI calls. There's receive, there is scatter, gather, loads of things. And that's quite a lot. So what you'll end up with is m types times n MPI calls, so you'll have m times n specifications to write. And then we haven't even thought about the custom types you may not thought about yet. You have to write one every single time. And you have to write one every single time for every single MPI call. And that's not a great situation to be in. So instead, we can use class traits to tell our function how to handle the different types. So instead of writing multiple specifications for this send, instead we're going to add a new static member to a data type traits class. We don't provide any default definition. That's quite important, which means that if there's no generic way that we can always make an MPI data type. So we're going to say, and it's quite important because it means that if it isn't specified, it's going to fail. And it's going to fail at compile time and give you a nice error, which means you know what you're doing. And now instead of providing a specific data type, you're going to return a type back, which is of a MPI data type. It's going to get returned when you call get. And now, when you provide a specialization, you just need to write out what the conversion between your type and your MPI type is. And that's just a list, just a mapping between the two types. And that's just a list of type objects, which can be used for every single of one of the MPI function calls, which you'd want to wrap in your communication class. Therefore, we have used type traits to inspect this in order to gather information and reduce the amount of work we have to do. And again, if a data type isn't implemented, we'll get a compile time error. So this is a nice way you can manipulate types to reduce the workload and the amount of code you have to write. If you're not familiar with MPI or haven't got experience using it, this may seem a little bit complicated, but just sit down and think about this more abstractly in terms of conversion between two sets of types. And that will probably make it a bit clearer. Additionally, those who have may be interested to learn more about MPI, we run a separate MPI course that runs at least once a year, if not multiple times. So look out for that on the ARCHER2 website, and it will be advertised quite usually and quite regularly. It's quite popular. So by all means, sign up to that if you want to learn more about how to actually use MPI to communicate between processes or between nodes and scale up the types of simulations you want to do. That course focuses less on things like C++ and more on C and Fortran, but ultimately you can just use the C examples inside your C++ code. What it doesn't do is necessarily discuss MPI and templates and things like that. Okay, so that is that section of lectures complete. Right, we're now 11:45. I wanted to find the example that goes with this. So, right. So the example for this is to look at the exercise. Let me just grab that. Exercise.cpp. So this is in the same set of exercises as before. It's underneath algorithm. And the exercise is to look through this and fill in the blanks using various algorithms. There's a couple of lambdas defined for things like generating random numbers. And you're asked to do a number of steps. So you have a section which says your code here in each section, which tells you what to do. So you need to go through this line by line and add in the missing calls to certain algorithms to progress this through all the options. And basically what it ends up being is you calculate some random numbers and then you also determine the Fibonacci sequence in the example. And then finally generate a sum. Now you can do all of this using the algorithms in the standard library. So I would look at CPP-ref, CPP algorithm, and CPP-ref, CPP numeric algorithms. Sorry, CPP numeric. There's a numeric algorithm section in there, which you can then call and try to apply this to that example and see what you get. What I suggest we do is we'll stop now. I'll hang around for 10 minutes for any questions and try and think about that template in a lambda function question. We'll take lunch slightly early from 12 till 1, and we'll come back at 12 o'clock and I will discuss the solution. So I come back at 1 o'clock and we will discuss the solution to this exercise before we move on to looking at eigen, which has a bit more of an involved exercise at the end. And then to finish the day, we'll have a slightly shorter lecture on threading in C++, looking at things like mutexes and lock guards, and then a final example. Okay, any other questions before we break to look at the example and have some lunch? Okay, I'm actually going to say we'll meet back at 1:15, so it gives you guys some time to actually have a break today. Otherwise, you're just kind of trying to work on things over lunch itself. So 10 minutes now and 15 minutes after lunch. Thank you everyone for this morning. If you have any other questions, please post them in the chat. I will look at this one now over lunch and come back to you. So apparently there's a question on ZMQ for C++. I've not heard of ZMQ, no. So the kind of, it may be much easier to implement than MPI for Pi. That's not a surprise. MPI for Pi was a little bit of a one-man band for a while, and then gained a great community usage because a lot of people are now programming in Python. And then the person involved kind of stopped maintaining it. My understanding, it's been picked up by other people now, but MPI is a bit fun. It's fair to say. What you had in the 90s, before everyone kind of settled on MPI, is a variety of other message passing interfaces which did this in different ways. ZM, I do not know them very well. I'm not that old, so I was still very much at school in that era. But it may be that this is a derivative of one of those message passing frameworks that existed. And it's a newer generation of one of them. MPI is a bit the standard. It's all well and good to use these other frameworks, but the question you have to often ask yourself is what is going to be supported in my computing center that I'm using if I'm trying to scale up? And if I don't expect support, and people don't tend to support beyond MPI because it became the de facto standard, you may be left supporting yourself. So just be wary of that with any comment there. Okay, stop now for lunch and I'll speak to you all at 1:15.